Today, Robert continues his work as the missions manager for the project carrying out humankind's last mission to Mars. So please join me in welcoming Robert to the stage.
Thank you, Brian. Thank you to the PTC user board for having me. Really appreciate it. Quick clarification on that. It is not the last mission to Mars, it's the latest mission to Mars. Yeah. All right, so first making sure I'm good to go here. That looks good to me. Can you all hear me in the back? Great, thank you. So in the next 45 minutes, make sure I've got a clock. Yep, good to go. I hope to show you some magic. So Arthur C. Clarke said in his book of essays, any sufficiently advanced technology is indistinguishable from magic. And I would claim that that's what you all do as well in your work, transforming the physical world with digital technology. So NASA's mission to Mars actually began in the 70s. We had a couple of exceptional spacecraft explore the solar system, and they are now outside the solar system, continuing to see what's out there. That's the Voyager missions. And we landed 2 landers in the 70s, in 1975, the Viking landers. Since then, we've landed 5 rovers. I actually started working at the Jet Propulsion Lab the week that the Sojourner rover landed. I started on Monday, and it landed on Tuesday, and that was a heady experience for me. So fast forward, I worked in research robotics and then got to work on the Perseverance, the Curiosity rover, and now the Perseverance rover for several years, as Brian mentioned. So here's our family of rovers. We started with a microwave-sized rover in 1998, and its prime mission was 30 days. 1 month, and it lasted 3 months. And then the Mars Exploration Rovers Spirit and Opportunity had a prime mission life of 90 days, and they're solar powered. And after several months, we expected the way that they would fail is too much dust on the solar panels. Mars is very dusty. And lo and behold, dust devils came along and cleaned the solar panels off. And Spirit lasted 9 years on Mars, and Opportunity lasted 15. So wonders of engineering, I'll say. And then Curiosity rover. So the Mir rovers are about the size of a large coffee table. And then the next rover we built is the Curiosity rover, and that's the size of a small car and is nuclear powered. Small MMRTG on the back there, and its cousin or next generation is the Perseverance Mars rover, and that's the latest one that we landed a couple years ago, and I'll spend most of the time here describing to you what we've been up to. So our goal with Perseverance is really science objectives, and simply it is looking for ancient microbial life. So life that could have existed millions, billions of years ago, small version, something like a bacteria or virus or microbe. And we haven't seen any cows or trapdoors or trees or anything. So we're looking for signs of life that could exist or have existed. And of course, that's astrobiology. Further, and if we find something with the sensors we have on the rover, and I'll get into this in detail, the burden of proof that what we found is so great that it's not possible to send all the equipment to Mars that we need to prove what we found is what we found. So, long story short, we need to bring samples back to Earth and share them with every lab around the planet to do that. So we built an entire sample caching system on the front of the rover, which I will describe in great detail. And then last, we have a little experiment to prepare for human exploration on Mars. Here's our rover system in kind of cartoon form. with our 7 instruments. And so it's got a big, long 7-foot robotic arm on the front. It is 6-wheel drive, all-wheel drive, and it has a mast and several antennas for communicating directly from and to Earth and through orbiters. We have 3 orbiters that NASA runs and 1 that the European Space Agency runs, and we are able to forward information through all 4 of them. HDMI for the win. Okay. So our science payload, in short, is we have some very capable cameras on the mast. We have a remote spectrometer with a high-powered laser. So we induce destruction with a laser on a particular point 7 meters to 12 meters away from the rover, and then look at the spectra that comes off the smoke from what we vaporized. We have 2 very capable spectrometers at the end of the arm, a ground-penetrating radar on the back, so we can fire off measurements every 10 centimeters as the rover drives and try and piece together subsurface structure or hard spots, and an oxygen generation machine as an experiment, and then a complete weather station that the Spanish provided for us, and they are running it to this day. Back to that sampling and caching system. This was designed from scratch, and this was the biggest technological challenge for the engineering team. So designed a second robotic arm, which is inside the belly of the rover, and we have these tubes made of titanium that can contain samples that are about 1 centimeter in diameter, and an entire storage system and sealing station, volume assessment station, all the things you need to assess, image, and seal and store these tubes. So this is about 8 years of design and development that went into all the different parts of this, getting the instruments integrated onto the rover, working with our foreign partners to get everything together. So this is a little video here, and we'll see if my sound is good. So this is just an animation early on in the development that shows how we wanted everything to go. So we bring our robotic arm out, take a core sample using a coring bit from regolith or hard surface, and then bring that back to the rover. With Curiosity, we would pulverize material into a dust and then drop it into the body of the rover to analyze it with instruments. And with Perseverance, we have a complete core that's inside that tube. This is the bit carousel that manages all of the pieces and the bits that come out. And then here's the second robotic arm that puts the tube through its measurement, imaging, and sealing. Okay, so if you told us or the project manager, put together a capable rover that can drive 20 kilometers, carry all these amazing instruments, be able to do remote science, proximity science, store the tubes, and prepare them to be brought back to Earth, go. Oh, and land in the most dangerous Martian terrain ever, drive twice as fast as all the previous rovers, and as a bonus, take pictures of the landing events, make oxygen from the atmosphere. Several hundred engineers and scientists would spend 8 years of their lives building what's on the screen. So you package this whole thing up. So I will not spend the majority of our time here talking about that, and happy to chat in the halls after this. We'll focus a little bit more on the results of the mission, but design, development, manufacture, integration, integrating the smaller pieces into larger pieces, testing those, testing the whole mast as a unit, the robotic arm, and then putting it all together in a clean room so that we're not contaminating Mars, and also contaminating Earth with the return samples, so they're explosively sealed. Then you end up with a complete rover ready for its mission to Mars. And then we have a whole other team whose job it is to spend, again, about a decade figuring out how to land that rover on Mars. And so they put together this descent stage, we call it, with 8 Mars landing engines on it. And I will show you how those work. So the rover is tucked into the descent stage there as one package. So where did we send this thing? The way this works is we ask for comment, and we have a yearly, I think it was every 3 years there for a while, 2 years. All the scientists around Earth get a chance to contribute and tell us where we should send one of our rovers. And so we started with 48 possible landing sites, and then we had a big landing site workshop and trimmed that down to, I think, 18. And then a few years later, trimmed it down to 8, and then 3, and then raging debates about, those last 3. And Jezero Crater was the winner, and the landing site workshop recommended to NASA headquarters to land there, and NASA headquarters agreed. So this is an artist concept of what Jezero Crater could have looked like millions of years ago when water was still flowing on Mars. And there's an inlet channel, an outlet channel, and this giant lake that existed. Today, it looks more like this. So this is a little flyover that we put together of our landing site. So on the upper left, there's this flow of material. If you can see here. Is my mouse showing up on the screen? Great. That'll help for the rest of the presentation here. So we call this a delta. So about 50 kilometers of area was subjected to this flow, and this flow of material came into the crater here. And I'm not a scientist. I'm not an astrobiologist, but I know some on this project, and they say this is a good spot to go and look for past signs of life and anything that could be contained in there. So we landed near it. In fact, on the other side of this unit here. And our landing system was actually aiming for here, and we landed across here, which is great. We were able to go do some science down here. And then we brought the rover over to the actual delta itself. And this is a little deceiving. This is a large front, which we cannot drive up. And then we'll continue along the delta taking samples and doing science, and then up to the crater rim itself. All right, so you have this beautiful rover ready to go, and you need to get it to Mars. How do you land a 1-ton rover on another planet? Package it up into the nose cone of a rocket, and it's got a heat shield there on the front, and that slows us down using Mars's thin atmosphere from about 10,000 miles per hour to about 1,000. And then we have a large hypersonic parachute, the largest one ever made, that slows us down to hundreds of miles per hour. And then we activate those 8 Mars landing engines, which I described, and bring us down closer to the surface. And now, actually, let me pause that. There's a key moment here that I'd like to show you. We lower ourselves on a sky crane using 3 mechanical cables and a data cable. And the reason is you get something with that much weight coming down right down to the surface. You need a lot of force coming off the engines to lower that much weight, right? That much inertia. That much force can kick up rocks and dirt right up into the whole system, blast the instruments, and damage our whole thing, our instruments, different mechanisms, before we even get a chance to use them. So we use this technique on the Curiosity rover as well. We hover and then lower the rover on mechanical cables until the rover's on the ground and far away from the engines, and then sever the cables and fly the engine away. So it's quick there, but an important piece. Okay, so that's what we wanted to happen. So one more note for you, and then we'll see what actually happened. We are landing in a dangerous place on Mars. So usually, we just have a landing ellipse and look from orbital imagery to figure out that everywhere in the landing ellipse is safe. But we really wanted to get close to this Jezero crater, so we put together something called terrain relative navigation, and essentially we have an FPGA on the rover, or these spacecraft looking down, and stored images of the terrain that we're going to be landing in or near. And while coming down, the vehicle is comparing live imagery from a downward-looking camera to the onboard imagery, and is able to then do a divert, if needed, away from any of the rough or hazardous spots in real time as it's landing by itself. Okay, so here is landing day.
We are starting the straighten up and fly right maneuver.
And so
where
we
the
had
spacecraft will jettison the
several
entry
folks from
balance
headquarters
masses
with us
in
that day,
preparation for
and this
parachute
is
deploy
the
and
entry,
to roll
descent,
over
and
to give
landing
the radar
team.
a better look at the ground.
Okay, so here's the parachute deploy.
Shoot deploy.
And there's a
The
slower version on
navigation
the
has
left.
confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
And, sorry, I'm going to go back to that, speed this up a little bit.
Kilometers of the surface of Mars.
Okay, so these are real-time images taken from
Perseverance is
COTS
continuing
cameras
to
looking
descend on the
downward
parachute. We are coming
of the surface of
upon
Mars. This is,
the
if you were coming
initialization
down,
of
at,
terrain
the
relative
first
navigation
human to come down to
and
Mars looking
subsequently the
downward, this
timing
is
of the
exactly
landing
what it would
engines.
look
Our
like.
current velocity
So we're on the
is
parachute
about
still,
90 meters per second
and then shortly
at
the
an
back
altitude
shell
of
with the
4.2
parachute will be
kilometers.
released, and we'll fire up those engines and do a divert to the side
We have
to make
confirmation
sure that
the
we don't
wind
hit
division
the
system has
back shell and the
produced a valid
parachute.
solution and part of terrain relative navigation.
Rhyming. TBA is nominal.
We have timing of the landing engines.
Right
Back
there.
shell set.
Current velocity is 83 meters per
And
second
a
at
divert
about
over to the
2.6
side.
kilometers from the surface of Mars. We have
And then
confirmation that the
back.
back shell has separated. We are currently performing the divert maneuver. Current
And from
velocity is
all the
about
exploration
75
we've done
meters per
since
second
this
at
was
an
done, I
altitude
recognize that
of
crater
about a
there.
kilometer
Okay,
off
so
the
we're
surface of
coming down
Mars.
now on our landing
Here in
engines.
safety Bravo.
Back shell and the parachute are far away, and
We
we
have
in fact
completed
found
our
them
terrain
later
relative
with the rover and
navigation.
took some pictures of
Current speed
them.
is about 30
And
meters
now we're
per
getting
second,
closer to the
altitude
ground
about
and getting
300
ready for that
meters
sky crane
off the
maneuver.
surface of Mars.
And
We
you'll
have
see
started our
dust getting
constant
kicked up
velocity
here.
accordion, which means we are conducting the
Okay,
sky
I'm going to
crane.
pause this right here. So, kind of late in the game in the development of this, we took some commercial off-the-shelf cameras and kind of as a nice to have. They didn't need to definitely work. We just needed this to land successfully. But we put one on the bottom of the heat shield looking down, the bottom of the sky crane, and on the rover looking up. And then we downloaded images from all those for months after landing, and you're going to get to see all three cameras at the same time with all the video put together of the final landing
Check the sky
maneuver
crane
here.
maneuver. Sky crane maneuver
So
has
there
started.
is the cables, and you're going to see the digital
About
cable
20 meters
sever,
off the
so we'll
surface.
lose one of the images, and then we will fly the landing engine away as far as possible, and it will crash land
We're getting signals
destructively
from Arnold.
away
Tango
from the
Delta.
rover. And
Touchdown
there goes the
confirmed.
engine.
Perseverance safely on the surface of Mars.
And all the
ready
humans
to
went
begin
nuts.
seeking the sands of past life.
So imagine for a second that you've worked on something, you got your CAD tools out or your circuit board analysis tools, and you worked on this thing for 8 years, and it's all pieced together and integrated together, and it's made it 200 million miles, and over a 7.5-year period of time, you get to find out, hands off the joysticks. All this needs to happen autonomously because the speed of light, which I'll describe. You get to find out whether it survived or made a new crater on Mars. Do you have a job the next day, or we'll have to go try again? So that was the reaction that you saw there in the control room. We also asked one of our orbital partners to redirect the orbit of the spacecraft to exactly coincide with those 7 minutes, and they were able to get an image mid-landing, and this is it. So this is Mars here. Here's us coming down, and here is a zoomed-in close-up with the parachute and the spacecraft inside. I mentioned those COTS cameras. This is one of the single still frames that we got back the next day, and just mind blown. We've never seen anything like this. So, this is as if you were in the descent stage looking down at the rover, and it had lowered on that sky crane, and we're just about lowered it to the ground. You can see all the dust kicked up. So just surreal stuff for us. And we've never seen anything like this during our landing experiences. And then, of course, we got to see our parachute deploy at 30 frames per second for the first time ever. And I don't know if anybody out there knows this, but there's a hidden message in the parachute. Maybe some of you know. And so I'll check at the end of the talk here, and I'll work out some prize for you. No cheating. I don't know what the prize is. Just made that up. Okay, so we landed this thing. So this was my view that day. I got to be the mission manager on landing day and took the keys from the landing team 20 minutes after landing. And so the left side is my terminal. And these are the first images that we saw from the rover. And so just spectacular stuff. Very excited to see that we survived the landing and that we actually have a mission. And this is a picture from our amazing mast-mounted imager and instrument. It's got different zoom capability, and so you get some depth of field there. So this is what we get to explore. So we were super excited about that. And then the next job was check out the system and see if it survived. So we wiggled the wheels, unstowed the 5 degrees of freedom robotic arm, and then attempted our first drive. So, we get to see if our motor control system is working and all the electronics in there, all 6 drive motors. And we find out if we have a rover, not just a lander. Big difference in those missions, right? Okay, so this is the simulation of the drive that was to happen before we send up the commands. Drive forward, do a gentle left turn, and then do a 360, actually that's a 180, reverse, and then take a picture of where we drove. So here's an image from the end of the drive, and if you look closely, it looks like this vehicle came out of the sky, landed on this terrain, drove forward, took a slight right turn, drove some more, and then did a 180. And of course, it did land out of the sky. That's exactly what happened. We checked out our sampling and caching system and the interface and everything that you saw in that animation, and took the panel off the bottom that protected the system, and there it is inside with everything survived. And so we have a mission. We're ready to go. All the hardware is good. We took out the robotic arm and took images with our close-up imager all the way down to the surface. So just for perspective, right? Mars and Earth orbit are different at different times of the year, and so they range from 35 million miles away to 250 million miles away. So when I'm talking to grade schoolers, I tell them, my family likes to drive to Yosemite, my wife and I, and it takes us 6 hours to get to Yosemite at 60 miles an hour, covering, about 300 miles. So if you started driving to Mars at about 60 miles an hour, one way, it would take you 100 to 400 plus years to get there. And we're able to go look at a piece of Mars from millimeters away because we found this interesting surface, and we all get to see it from 400 million miles away in 20 minutes at the speed of light. Okay, so next part of the mission was we dedicated several weeks to a little technology experiment called Ingenuity the Mars Helicopter. So tucked into the belly of the rover, which I forgot to show you earlier in those pictures, was this protective pebble shield, we called it, and inside is a little dual rotor flying system. So we spent a bunch of time deploying the legs and getting it ready to drop it to the surface. And we had a very compelling day in our mission because if we didn't After severing Ingenuity, dropping it to the surface, if we didn't drive the rover away from on top of it and expose the helicopter's solar panels to sunlight, it would die within 40 hours. So imagine getting this whole thing together, getting it to Mars, and then it's DOA before we get a chance to try it out. So we did a very special day, which my team spent months working on. We were able to do direct-to-Earth communication straight from the rover, which is very low bandwidth. It's 200 bits per second directly from the rover to us, as opposed to through the orbiters. 200 bits, not kilobits or megabits or gigabits. 200 bits per second. And with our 200 bits, we were able to figure out that it was doing the right things and we didn't have to intervene. And we successfully got Ingenuity deployed and ready to go. So there's the solar panels and a healthy helicopter. And then we drove the rover a safe distance away. At least 45 meters is what we were using. But before doing that, we took a selfie to celebrate the fact that both vehicles made it safely to Mars. And in case folks are wondering why we use, how we do a selfie, we have a camera at the end of the robotic arm, and there it is on the lower left, and we take about 50 images at different vectors and piece them all together, and you end up with this beautiful image on the upper right. So there's our family photo safely on Mars. There's the rover tracks where we dropped off the helicopter. Okay, so time to try this thing out. Technology experiment. We did a low-speed test and then a high-speed test of the rotors. All systems were good. So, so to be clear here, before this moment, humans had never flown on another planet. To be very precise, powered flight on another planet, because technically when we're coming down with spacecraft, that's kind of flying, we can do diverts and stuff. So this is the first attempt at powered flight on another planet. This imagery was taken from the rover from 50 meters away. So I was in the control room that day because I worked a lot with the helicopter team, and I went and stood behind our imaging expert, and these frames from this flight were coming down, and I saw it pop up in the air because we were missing some frames, and I was going, oh my gosh, okay, now please land, please land. So it flew up to 10 feet, rotated 90 degrees, hovered for a little while there in the Martian breeze, and then dropped down and did successfully land. So now, thank you. So now we can say that we and you all can fly on other planets. So very simple flight. And then after that, the whole purpose of that technology experiment was what you just saw. The team could declare success, margaritas, put it on the resume, done deal. But we did have 4 more flights planned in case it survived. It did. The next flights. I need to show you
Spin down.
the team's
Altimeter
reaction there.
data confirms that Ingenuity has performed its first flight.
These are exciting days for us. They're all exciting days, but a couple are in particular are pretty exciting. Okay, so that's when I first saw the imagery. So there's a picture from the copter. We've never seen this before. There's a leg in the upper left and rover tracks where we were using it to position the helicopter. And here's another view from later in the mission. We actually started using this for some science exploration. And so this is a picture of Mars from the helicopter. So after that first flight, we flew it higher, did some lateral motions of a few meters, and then 50 meters, and then 100 meters. Those were the first flights. And it survived those. And so I had told everybody who would listen that it might survive and we need a plan. And they didn't want to do a plan. And so I was then told to make a plan once it survived. So we did. And As of last weekend, we have done 72 flights with Ingenuity. So imagine you're standing on Mars, and you're one of the first astronauts on Mars, and you've sent off your scout to go, see over a hill or go somewhere where you can't drive or send the rover. I'm going to speed this up, and if you look on the right side of the screen, you can see a dust devil moving across. Hopefully that's coming across on the screen there. So there's weather on Mars, and dust devils, and all kinds of fun stuff. So you're standing there, looking at the view and this panorama, and then your little scout comes back from the job that you sent it to, and there she is. So traveling at about 5 meters per second, and she'll now fly up to 14 meters up above the horizon and then land. So this is what flight on another planet looks like. When I first heard about this in 2015, I was thinking, hold on, Mars's atmosphere is 1/100th by density of Earth's atmosphere. But if you make really fat carbon fiber blades and spin them at 5 times faster than an Earth helicopter, you can get enough force to carry a lightweight body. That is, let's see, the record for any helicopter on Earth as far as height above sea level is 42,000 feet. That's the highest any helicopter has flown on this planet. And Ingenuity is flying at the equivalent of 100,000 feet. So we broke the height record by double by trying to figure out how to fly on another planet. All right, here's the view from the helicopter itself. This is the black and white navigation camera, and we use this to track features that are going by at 30 frames a second, and that helps us figure out absolute localization. We have gyros and accelerometers to figure out thousands of times a second what's happening with the vehicle, its attitude, but those drift. So we need a way of calibrating against Mars, and so we're using a visual method with an FPGA. I think it's just using a regular processor for that. So that's what it looks like flying across Mars 12 meters above the ground. And here's just kind of a little greatest hits video from a year ago of different views from the rover of the helicopter in action. So over those 72 flights, we have now flown 17 kilometers of distance and have greater than 2 hours of flight time with this little tech demo that was supposed to fly once. Those green and red were the feature tracking that I was describing. And here's one of the landings. Okay, so that's our technology demonstration of flight. We have another one that's on the mission called MOXIE. To make a long story short, some folks at MIT, when we were putting this instrument on the rover, I think only years before, they had figured out how to take a stack of metals and using electrolysis and putting some electricity in there, they can take in CO2, carbon dioxide, and spit out oxygen, pure oxygen. And so we made a smaller version of that that's not on a laptop, packaged it into the rover, and got it to Mars, and then ran that experiment, and we have generated, I think, more than 60 grams of oxygen, which is enough for a person to breathe for about half an hour. And so we can say we've started terraforming Mars. We made this much oxygen, but very successful experiment, and that's for the human exploration directorate so we would scale that up for humans to be able to just breathe oxygen straight out of the atmosphere using that technology. So a few more things onto the, so I actually, let me just double check with the board here. I heard that we can go past 9, but last night not so much. You give me a hand signal on how much time we have past 9, okay? Okay, great. So mainline science mission here. This is a picture using the robotic arm right up close to the surface. And again, I was on shift one day and I grabbed this image because I just couldn't believe my eyes of what I was seeing on the screen, that we get to see something like this by nature of this whole engineering marvel. So that's the up-close image from the end of the arm at this interesting little area that then we took samples of. So the way this works is we drive into a new area, we take remote science pictures and use the laser spectrometer, and then if we find something of interest or the scientists like the area, then we unstow the robotic arm and look at things close to the ground. And then we have an abrasion tool that we can use to take the top surface off of something, and then we blow it clean with a little CO2 blaster called the gas dust removal tool, the GDIRT. And this is what you get with one of those really up-close images after the abrasion and the blast has operated. Really interesting stuff. And if the scientists like what they see then we decide to take a core sample. So this is the unstowing the robotic arm and taking a core with the drill. And so this is the first borehole that we took with the mission. And because we needed to be so efficient with this mission, we can autonomously take the core sample, bring it up into the rover, take it into the processing bay, measure it, image it, seal it, and it's done all in one day. So we ran that whole operation because we checked out all all those mechanisms, and I came in to work the next morning, and I wasn't on shift, and there was a ton of people in the room, and I walked in and asked my friend what's going on. He said, "The tube is empty. We have sealed it forever, and there is nothing in it." So that was, I'll say, the first engineering challenge of the mission. You could also call it a failure of engineering imagination on Earth. I went home that day and told my wife what was going on. She was, gobsmacked, and she said, "You mean Mars didn't let you have it?" It's like, no. It just, something happened to this. So we spent several days trying to figure out what happened. And very long story short, the material we first tried was very granular, and it had voids in it. And the drilling operation just pulverized it. So there was no hard core left. So then when we pulled the core out, all the material just fell out around the hole. And so, we had folks geometrically figuring out how much volume was in this little powder pack around the hole, and it was about the right volume. Okay, so even though we tried this on 87 different rocks here on Earth, we picked the wrong one to try first on Mars. Mars always surprises us in some way. So we found an easier rock for our first drilling operation, and that worked great. And so this is the first sample that we got that's inside the drill bit there. And on the upper right, you can see this exceptional range of material in there. So that is being brought back to Earth at some point in the future, which I'll get to in a second. We get to get our hands on that piece of material that a world-class team of scientists from around the world decided we should get that sample, document the area around it thoroughly with different instruments and spectra, and bring it back. And so we had to celebrate by taking a selfie. So there's 2 holes there on the rock. We took a double sample, which I'll describe in a second. So we did some good science, got our first samples down where we landed, and then we decided to motor over to the delta, which I described, this big wash of material, and here's the edge of the crater. And so another team that I got to the pleasure of working with for years put together a whole driving system where we have a separate processor. Actually, we're using the same vision processor from landing, and we repurposed it with a new FPGA burn to do all the stereo, the intensive stereo processing and figuring out the range of things in front of the rover. And so we kicked that off and let the rover drive several hundred meters by itself. We can only see about 50 meters with humans directing it, so we call it directed drives. And then beyond 50 meters, we can't see what the terrain is like, so we need to rely on it to drive itself. So over a weekend, it did all this driving by itself, avoiding obstacles. So once per